Hi, my name is Mingshuo Liu, and I will introduce the fourth and the fifth part of our paper. The fourth is experiment planning. 4.1 is subject selection. We test five libraries. The scikit-learn intellects, XGBoost, PyTorch, and TensorFlow. They're active and easy to install from Conda or PyPL. They cover core tasks, the classification, regression, and clustering. They allow fixed random seeds. They run on our machine without special patches. And you can see it on this table. Is the reason why we choose these tasks and these libraries. For the 4.2 is experimental variables. The independent variables is library, hardware platform, algorithm type, disk size, and the dependent variables is energy, runtime, accuracy, quality, memory, and utilization. The dataset size has three levels: small, medium, and large. This shows scaling and thermal effects. The 4.3 is experimental hypothesis. We make two big research questions. The first one is energy usage across different uh, libraries. And the second one is energy performance trade-offs. So we divide the second one into three parts. The 2.1 is energy memory trade-off, and the second one is energy versus runtime, and the third one is energy versus utilization. We also pay attention to the uh, library with hardware interaction. For the 4.4 is the experiment design. We use a mix factorial design with partial nesting. Not all algorithms exist in all libraries, so the design is unbalanced. We randomize the order of library hardware algorithm combinations. With a combination, we run small, medium, then large data size. For each treatment, we repeat 20 times with a fixed seed. The power analysis supports this for medium effects at 0.8. Polarized brands show coefficients of variation under 50%, 15%. Thermal control is strict. We warm up for 90 seconds before major runs. Also cool down for 3 minutes. 3 minutes after each run, we run until we will wait until the temperature and power return near balance. The estimate while time is about 50 hours, including cooldowns and overhead. The 4.5 is data analysis. For the phase one is data exploration. We will report the mean, median, SDIQR, CV, and show the histograms and box plots, mark outliers with the IQR rule and note reasons. The phase two is assumption check and hypothesis testing. If it's normal and equivariance, we will use one-way ANOVA and Turkey for recent question one. I see here. And Pearson for recent question two. The two-way ANOVA for the library and with hardware. If it's not, we will use crucial volleys for recent question one with the dance with speech and the experiments for recent question two. For the phase 3 is the effect size qualification. We'll use the coherence, the eta squared, and Pearson's. For the non-parametric is the Cliff delta. And the fifth part is experiment execution. The 5.1 is setup. We will run one laptop on AC power. Use Ubuntu, the laptop with Intel Core and NVIDIA GPU. We will use the experiment runner to orchestrate runs. We will use the PS to sample CPU and memory. We will use the energy bridge to capture energy. We pin the Python dependencies, the secondary instance-level attributes, and torch. We apply a undefined power policy. We disconnected non-issue out device, and after each run, we will queue the process and clear caches. The 5.2 is architecture. The experiment runner is the controller. It starts module code and energy sampling together. A performance module computes task matrix after each run, accuracy for classification, mean squared error for regression, the similar score for clustering. The experiment runner then merges energy, runtime, utilization, and performance into one record. It appends the record to the run table CSV is the output. The file will use to the R analysis. The 5.3 is preparation. We run offline. The dataset and models live on live on the local SSD. We keep a public repository with strips, seeds, and configs. Anyone can repeat the experiments on the other machine. Before the main runs, we do dry runs. We check for stability. We turn warm up and cool down if it needed. For the measurements, sampling rate is 1 Hz. Total energy equals the final cumulative reading minus the initial reading for each domain. The time samples give runtime with millisecond precision. The PS2 samples CPU percent and memory megabytes each second. We keep sampling aligned with energy. If a run crashes on the operating system interface, we mark the raw, the investigate cause. We remove the raw or keep it with a note based on evidence. For the execution order, okay, you can see the table 4. We include 13 valid algorithm library hardware combinations. Each combination runs on small, medium, and large data size. Okay, see that one. We keep on 90-second warm up before the major runs and 3 minutes cooldown after each run. Just reduce the thermal drift. The plan table lists all configurations. It matches the rows you will see in the logs and in the run table point CSV. Okay, that's all my part.